When a child presses the car's accelerator, and at the same time a parent is using the remote control, who's in charge? Well, today is part 3, where we finalize our decision architecture and implement an authority router, the layer that decides who owns the car's speed, direction, steering, and power. Welcome to more Little Man Builds. We pick up from last time where we had implemented the ConfigBus. Today we're going to amend Control Core and Power Drive Handler so they manage commands more safely. Then we will introduce another decision layer, the Authority Router, that tells the car what it is allowed to do based upon set policies. Those decisions are then sent to the Control Core, where the commands are built into a snapshot and sent via the Control Bus. Now there's one strategic element I have built into the design, and that is the Authority Router also subscribes to the RC publisher. Let me explain why. When the car powers on, it reads the hardware inputs through the MCP23017. That gives the software raw electrical states, switches, buttons, and selector positions. The dip switch is the first important configuration input. It selects the vehicle mode. The first mode is full RC, where the parent controller owns everything: steering, direction, speed, and power. The car brain still sits in the middle, but it mostly says the RC is allowed to drive provided the signal is fresh and not in failsafe. Now there's some other key details here. The parent must set the vehicle power to be greater than 0, otherwise the car won't move at all. This is an important safety feature because at any point in this mode, they can adjust the overall power as a percentage that is being fed to the wheels. If the speed has been set but the direction stick is centered, the drive request stays neutral. The parent must give an explicit forward or reverse direction for the car to move. The reverse is also true. If no speed is set, a forwards or reverse request will also result in no movement. In this mode, the parent also has the ability to delegate ownership to the car, but at any time can immediately switch this back to position 0 to regain control. Mix mode, or position 1, delegates steering to the car. Power steering and how this is managed will all be addressed in a later episode. Delegated mode, or position 2, gives steering and speed control to the car. Now the gear selector is no longer just information, it actively limits or blocks movement depending upon which setting it is in. Joystick mode will be similar, except this will be for disabled children. We'll also implement this in a later episode. The fixed modes are direct drive profiles and are not influenced by the RC. The dip switch chooses the maximum allowed base power, 40 through 100%. The gear selector then applies a second limit by dividing the total power into 3 forward ranges, D1, D2, and D3. And of course, there's also reverse. The car in this mode is obviously driven by the accelerator. So the full story is this. Inputs report what they see, Config Publisher turns raw switches into meaningful mode and gear, RC Publisher turns RC signal into trusted intent, the Authority Router decides who owns each part of the car and what limits apply, the Control Core builds the actual command, Power Drive Handler executes that command safely with ramping, drive enable, and handover protection. So now let's go and actually build it. So the first file to update is the Authority Bus. Before writing the router, I want to define what the router is supposed to output. This is important because the output shape tells you what the system cares about. So the first concept is the owner. An owner is the source that currently controls one axis of the vehicle. The owner can be none, RC, direct, or joystick. None is the safe or the fault state. RC means that the remote controller owns that axis, direct means that the physical child-operated inputs own it, and joystick is reserved for assistive joystick control, and this will be for disabled kids. Then there is the RC delegation. This is how the parent controller can choose how much control the RC keeps. Full RC means the remote owns steering, speed, direction, and power. Mixed means that the RC keeps the speed, direction, and power, but steering can be localized to the car. Delegated means the child or local system owns steering, direction, and speed, while the RC keeps the power authority. And doing it this way means it's much more flexible than one big RC on-off flag. Then the authority snapshot brings it all together. It contains the selected mode, the selected gear, the delegation policy, contains whether RC is in failsafe, and then it contains the actual ownership decisions. And the key idea is that authority is per axis. That is what lets the project scale. The parent can own power, but delegate steering. The parent can own speed, but allow local steering. The child can own speed while the parent retains a kill or power authority. And because all of that is represented in one snapshot, the rest of the system can read one decision instead of resolving the policy every time. So next, let's add an authority policy. This file holds the name policy values used by the router. The important values are for the mode caps and the gear caps. A mode cap comes from the selected driving profile. For example, a dip setting might limit the vehicle to 40, 55, 70, 85, or 100%. A gear cap comes from the selected gear. Drive 1 might be slower than drive 3. Park should prevent movement when the local gear selector is actually part of the drivetrain decision. The unknown gear should also be safe when gear is participating. The router combines these into an effective cap, and I like separating this into a policy file because the router should not be a dumping ground for all these magic numbers. If I want to tune first gear later, I can just change a named value. I should not have to dig through ownership logic to find a random 0.4f buried in the middle of a switch statement. So this file makes the decisions easier to read and easier to tune. By the way, if you're enjoying today's content, smash the like button or please consider subscribing. It really helps me out with the algorithm and I'd love for you to join our community. So now we can introduce the new decision component, the AuthorityRouter. The header makes the responsibility very clear. It consumes RcBus, ConfigBus, and publishes AuthorityBus. That's the job. It does not read MCP pins, it does not debounce switches, and it does not drive the motor. It does not generate pulse width modulation. It sits between clean inputs and command generation. And that is why I like the name router. It routes authority. It decides who owns what. And later, if this project grows, this is where more decision sources can be added. Obstacle detection, joystick enable state, service health, parental override, app control, or other future features should not end up scattered through the motor driver. They should feed the decision layer. So the CPP file is the main one for the episode. The router starts by reading the latest RC snapshot and the latest config snapshot. It uses the snapshot bus fallback helpers, so a single unstable read does not make the whole control system behave randomly. Then it checks liveness. If the RC is stale or in failsafe, the router does not pretend everything is fine. It marks RC as unsafe and uses a safe fallback instead. If the configuration is stale, the router does not guess the gear. It forces gear unknown. Now that is important because unknown gear should not create movement when gear is participating in the drivetrain decision. Once it has a safe input state, it resolves the RC delegation mode. In this project, the RC mode channel can represent full RC, mixed, or delegated. That gives the parent controller a way to decide how much authority the RC keeps. Then the router decides ownership, and this is where the architecture really starts to pay off. Instead of control core asking, are we in RC mode, and then later asking, are we delegated, and then later checking gear and speed caps, the router centralizes the decision. It outputs the owner steer, direction, speed, and power. That means control core can be much simpler. It just asks who owns the speed and who owns the direction. Then it builds the command from the selected source. The router also calculates speed caps. There is a base cap from the selected mode or from the parent power setting. There is a gear cap from the selected gear, and there is an effective cap after combining them. But there is one important nuance. The local gear selector should only be a speed limit when the local drivetrain path is actually participating. If the RC has full control or if mixed mode is only delegating steering, then park on the physical shifter should be visible as context, but it should not be displayed as if it's actively limiting speed. That distinction makes the debug output much less confusing. And this is the important separation. The authority router decides the limit, control core applies the limit, and power drive handler executes the resulting command. Decide here and execute somewhere else. This is the key principle of the episode. So let's quickly just update the app policy. We also need to add something for the authority, and here it must be also fresh to trust, and it's pretty safety critical. So let's put this at 150 milliseconds as well. Because the authority router is now a real active component, it gets a task descriptor. And this is logic side work, not input side work. So it runs as a logical task on the control side of the application. The exact stack size and priority can always be tuned, but the important thing is that we keep the consistency across the project. Every major task has a clear name, priority, stack allocation, and core affinity. That makes the system easier to reason about and easier to debug. Now let's update the control core. So it already had a connection to AuthorityBus, but before this episode, that authority state was basically a placeholder. So now it becomes real. The important conceptual change is that the control core is no longer the mode decision maker. So it simply is the command builder. It reads the buttons, the remote control, the authority, and then it creates a control snapshot. That is a much narrower, cleaner job, and that makes it much easier to test, explain, and extend. Now for the CPP file, the control core implementation changes because it now obeys authority snapshot. First, it reads the latest authority decision using the same stable snapshot bus pattern. Then it checks whether that authority decision is still fresh. So if the authority stream is stale, it does not keep driving from an old decision. It creates a safe authority snapshot. That is, no owners, unknown gear, zero effective cap, failsafe equal to true. Then it reads the RC input and checks whether the RC is trustworthy. And that trust check matters. If the RC owns speed or direction, we should only use RC axes where the RC snapshot is fresh and not in failsafe. So the code wraps the RC access in a small trusted RC helper, keeping the rest of the function cleaner. There is also a new RC drive intent step. RC speed alone should not move the car. The parent has to make a conscious direction request. So if the RC speed is raised, but the direction stick is still centered, then there's no movement. Only once there is both speed and a valid forward or reverse direction intent can there be any RC-owned driving motion. So then control core looks at the owner speed. If the speed is owned by the RC, it uses the RC speed access, but only in combination with some kind of direction. If speed is owned by direct or the car, it uses the accelerator button. If speed is owned by the joystick, it currently returns a safe output because joystick control is not implemented in this stage. And if speed is owned by none, then it outputs 0. So then it applies the effective cap from authority snapshot. The source requests the throttle, the authority limits the throttle, and the control core combines them. And that is much cleaner than having every input source apply its own version of the limits. And direction works in the same way. So if direction is owned by the RC, the parent must make this movement on the remote control. If direction is owned by the car, then direction comes from the gear selector. If gear is reverse, then the command becomes reverse. Otherwise, it stays forward or safe. After that, the control core publishes the explicit drive contract. The throttle command %, direction command, drive enable, and the drive owner. Now, drive enable is pretty key here. It means that a direction like forward is not the same as permission to move. Movement requires a meaningful throttle input and a valid direction intent. Horn and indicators remain button-driven, guarded by button freshness. So now we need to update Power Drive Handler, and it is intentionally not the star of this episode, and that's a good thing. The motor execution layer should not know why a command exists. It should not know which dip mode is active. It should not know whether RC has delegated the speed. It should not know how gear caps are calculated. It should only receive a control snapshot and execute it safely. That said, the executor does have one important safety job. It honors drive enable and it tracks the active drive owner. And if the drive owner changes while the car is moving, it forces the output to 0 before accepting the new owner, and that matters for any kind of handover. Imagine the child is driving forward locally and the parent switches RC back to full control while the RC stick is already requesting forward. Now, without a handover interlock, the car could continue moving smoothly from one owner to the next, and that might sound convenient, but it's not what I want. Changing who owns the drivetrain should be a conscious transition. So the handler waits until the output has ramped down to 0 before accepting the new owner. It also keeps the existing direction change interlock, so a forward to reverse change cannot happen while torque is still being applied. That makes Power Drive Handler boring, but in the best possible way. The decision layer decides, the control layer builds the command, and the drive handler executes safely. Finally, main CPP wires the full system together. And this is where the project changes character. Before this, the project could read inputs and drive outputs. After this, it has a decision layer. That is the difference between a working sketch and a scalable embedded application. The code no longer asks the same policy questions in 5 places. It asks them once in AuthorityRouter and publishes the answer. Everything downstream gets simpler because the hard decision has already been made, and the safety story improves too. RC speed does not move the car unless the RC direction is intentional. Gear caps only apply when the gear is part of the active drivetrain authority, and any drive ownership changes must wait for 0 before any handover. Those are exactly the sort of behaviors that are hard to maintain when policy is scattered everywhere. Currently, we are in RC mode. We can change the overall cap to whatever power requirements are required, and also delegate. So we're in mix mode, so steering is with the car, but driving is with the remote control. And here you can see that we've now delegated full control to the car and the cap is set to 100. So again, we can change the cap, but currently we're in park, so let's change to D1, D2, D3, or we could also go into reverse. Let's change the display to drive mode, and this time I've actually plugged the motor in. So let's give the car a direction with the right hand stick and some speed with the left. The motor responds to any speed changes. If I quickly change direction, it should immediately ramp down, then ramp back up to full speed again. Let's reduce the speed to the wheels, increase it again, change direction, and while they're both at maximum, we can move to the overall power knob up here, and let's just decrease this a little. So this is a key safety feature because if we're not yet ready to drive the car at full power, we can adjust this to a lower level or to something that feels more comfortable. And if no direction is provided, the car immediately stops. Let's delegate full control to the car, so both steering and speed. If I press the accelerator, actually let's swap hands as that doesn't work. We can put the gear into D1, D2 or D3. You can see how the overall speed is divided evenly into each gear. Let's release the accelerator, press it again, and quickly throw the car into reverse. I'm still holding the accelerator here, but notice that the car waits for the motor to come to a full stop before changing directions. The reverse mode is speed limited to 40%, and I will actually ensure this is consistent across the remote control too, as currently it's not. Here's the power safety again, where we can reduce the overall power to the car even while delegated, and this ensures that the kids are always driving at a level where you feel comfortable. So I'll put it back to full speed. It's really not hard to imagine kids being naughty, so if they try to drive away, simply flick this switch back to regain control of the car. And now nothing at the car level works. Let's update the dip switch position and reset the ESP32. I've put the car into max 85 mode, so here this is where the child is a little older and you're confident they will listen to your instructions, or that's the hope. Now the RC has no influence over the car at all, and the child has complete control up to a maximum power of 85%. So let's see that in action. Let's press the accelerator and move the car through each gear. Again, just demonstrating that there's no control through the remote control at all. The motor still responds properly to any change in direction, always coming to a complete stop. So there's the full demonstration of how everything works. Today we gave the car a proper decision layer. The inputs report what they see, the authority router decides who can control what, the control core then builds the commands, and finally the power drive handler executes them safely. That way the project can grow freely without the motor code turning into a mess. The entire project is freely available on GitHub, link in the description. Smash the like button and please consider subscribing. See you in the next one.